Good afternoon to all of you once again. So earlier we discussed one result that if x comma d is a metric space and that metric space is sequentially compact, then that metric space is compact. And we also discussed the converse of this theorem, which also holds. So that means whenever we have a metric space x, then x is compact if and only if x is sequentially compact. So this result we have discussed earlier in the last lecture. And in the last lecture, we have defined one notion that is limit point compact. So topological space X is called limit point compact if every infinite subset of that set has a limit point in X. So we have considered this particular subspace of R. So A is a subset of R on which we are considering the subspace topology. Then A does not A is limit point compact or not? That is the question. So to check that is limit point compact or not, we have considered a particular infinite subset of A that is 1 minus 1 upon n. So all these points belongs to this particular set, close interval 0 to open interval 1. So all these points belongs to that set, and that is obviously an infinite set. So we know the limit point of that. So whenever we take limit, its limit n tends to infinity 1 minus 1 upon n is 1. So the limit exists of the elements of this set, but so that will ensure that 1 is the limit point of this set, but 1 does not belong to this particular set capital A, because capital set A is close 0 to open 1. If we take capital set A to be closed interval 0 to 1, then this limit point will be inside A. But for this particular set, it does not belong to. So therefore, this subspace A of R is not a limit point compact. And we also know that this is obviously not compact subset of R, because every compact subset of R is closed as well as bounded. So this set is bounded, but it is not closed. So therefore, it is also not a compact set. So A is neither compact nor limit point compact. So today we want to see some relation between compact spaces and limit point compact spaces. So first of all, these spaces we are basically studying limit point compactness. This property is also known as in the literature as Fréchet spaces. Fréchet compactness, or in real analysis it is known as Bolzano-Weierstrass property. Right. So we want to study this particular property and its relation with earlier notion of compact set. So that is very open cover as a finite subcover. So first result today we want to study is every compact topological space is always limit point compact. So note that we are not considering metric space here. We are taking general topological space, which may not have metric defined on that set. So what is given is we are given a compact topological space. So let X be a compact topological space. Then we want to show that X is limit point compact. Right, and then we know the definition of limit point compact space, that is every infinite subset of X has a limit point. So that is what we want to prove, that if we take any uh, any subset A of X which is infinite, we want to prove that it contains a limit point. So let us start with such a set. So given that A is an infinite subset of X, we want to prove that to prove X is limit point compact, we want to prove that whatever given infinite set A, it contains a limit point. So let us assume that our conclusion is false. That means suppose A has no limit point in X. Right. So later on we will get a contradiction. So that will prove that A has a limit point. So if A has no limit point, that means what? That means the set of all limit points of A is a null set. Right. So A is a subset of X, and the set of all limit points of A is null set. So therefore, what is A closure? By the definition, A closure is nothing but A union A dash. And then we know that A dash is null set. So that means this will be equals to A itself. Right. So A is a subset of X whose closure is itself. Right. A closure is A. So that will give us that A is a closed set. Because every set whose closure is itself is always a closed set. So we started with the assumption that A is an infinite subset of X, and it has no limit points. That means A is closed. So now A is a closed subset of X, and since X is already compact set, and in which we have a closed subset. Right. So A is a closed subset of a compact space. So that will give us that whenever we take a closed subset of compact space, we proved one result that says that every closed subset of a compact space is always a compact space. So since X is compact and A is a closed subset of X, A is also compact. So here we are using, because every closed subset of a compact space is also compact. So we proved that A itself is a compact space. Now what we will do is we will find the neighborhood of every point A in A. So for every element A of A, there exists a neighborhood. There exists a neighborhood UA containing the point A. Right. So this happens because even we can select a basic open set around every point A. Right. So every point A has a open set which contains that particular point. So that set we are denoting by UA for every A. So that means what we have a open set which contains the point A, and what we know is that the capital set A has no limit point, right? So the set has no limit point, that means every point in A is not a limit point. So since A is not a limit point, of capital A, so the capital set A has no limit point. So in particular, the points of that set itself is also not a limit point. Right. So we want to use a characterization of limit points. So if you remember that a point is a limit point if and only if every open set containing that point intersect with the set in a point other than that point itself. Right. So that we want to use here, that since A is not a limit point of A and UA is a open set containing the point A, using characterization of the limit point, we get that UA minus singleton A intersection A is phi. So if A is a limit point, then this intersection should be non-empty. But because A is not a limit point, this intersection is an empty set. Right? So using this, what we get is that basically we have a topological space X in which we have a point A and we have a neighborhood UA which contains that point, and then we have a set capital A which contains this point A. So this condition says that UA minus, when I delete singleton A from UA, its intersection with A is null set. So that means A does not contain any point other than A of UA. Right. So that means what we get is that UA intersection capital A is nothing but the singleton set A. Right, because A does not contain any point of UA other than singleton A, other than A. So that means intersection is empty set, intersection is singleton A, and this is true for every A, because for every A we are getting a neighborhood UA. So using this limit point condition, characterization of limit point, what we have done is we have found an open cover. So let us see what we have found. So note that every the set A itself we can write as a union of singleton sets. And then every singleton set is a nothing but UA intersection capital A. Right. So in fact, just a minute. So what we know is every point A belongs to UA. So let us first use that every point A belongs to UA. So this singleton A is a subset of UA, and then we take union both the sides, so we get this part. So now we have an open cover UA which covers the space A, right? So therefore UA, A belongs to A, is an open cover of the compact space A. We know that A is a compact space, right? And this computation will give us an open cover of the set A. So since the space is compact, every open cover has a finite subcover, right? So therefore what we get is that A is a subset of not the full union, it is contained in the finite union. So finite union means we can write this as U of I running from 1 to n, right? So the above collection might be infinite, but this collection is always finite because it is a finite subcover. So now using this collection UA of open sets, compactness of A, and the characterization of limit point, we are getting this thing. So let us use that. So therefore, since A is a subset of this finitely many union of UAI, so we can write A as A intersection A, right? And then we can substitute this particular intersection here, so we get A intersection union I1 to n U of AI, and then we can use the distributivity. So we get union I running from 1 to n A intersection UAI. So now we will use that computation because we get this set, so that we know that it is nothing but singleton A, right? So here we get, instead of A, AI. So we get UAI intersection A is singleton AI. So these two sets are same, and so finally what we get is we get the set A is a subset of this finite union, right? So finally what we get is that A is a subset of union I running from 1 to n singleton AI. So this is nothing but the set A1, A2, An. So A is a subset of this set, and this set is a finite set. But what we assume earlier is that A is a infinite set. So if you remember, we started with the infinite set A. So starting with infinite set A and assuming A has no limit point, we are getting that A is a finite set. Because every subset of a finite set is always finite set. So we get F is a finite set, which is a contradiction. It is a contradiction to the assumption that A is an infinite set, right? And then this assumption is coming because we are assuming that A has no limit point. So therefore, A has a limit point. So we proved that every infinite subset A of topological space X has a limit point in X. So therefore, X is a limit point compact. So we proved a result which is for the topological space. We did not use a metric in this proof. We just use that X is a topological space. So that means this result is true for topological spaces. Every metric space is also a topological space. But every topological space may not be a metric space. So this result we prove for the general topological space is that every compact topological space is always a limit point compact. So what about the converse? So converse is actually true for the metric space case. In general, it is not true. So let us see what if we can prove that for the metric space cases. So if you take a metric space X comma T, which is limit point compact. Then we'll show that X is a sequentially compact. So in metric space, we already know that X is a metric space. Then X is sequentially compact if and only if it is compact space, right? So sequentially compactness and compactness are equivalent condition for the metric space, whatever metric space we take. And we already proved that every compact space is a limit point compact in the previous result. So now we will prove that every limit point compact is sequentially compact, and that every sequentially compact is already a compact space. So that will give us the characterization of all these three conditions of compactness are equivalent when we take the metric space case. So let us try to prove this result. Then we will state this result, combine three conditions. So what is given is that X is a metric space which is a limit point compact, and we want to show that X is sequentially compact. To prove X is sequentially compact, we have to start with the sequence, and we need to prove that it has a convergent subsequence. So let us start with the sequence. So let Xn be a sequence in the matrix space X. So now we want to use the hypothesis that is that X is limit point compact, and to use limit point compact we need to consider an infinite set. So every infinite subset of a limit point compact space has a limit point. So using sequence we can consider an infinite set which contains all these elements of the sequence, right? So consider the set A, which is defined as all the terms of the sequence. So that is x1, x2, x3, so on, xn, so on. So this is basically an infinite set, right? So consider the infinite set, this one. So since this is an infinite subset of a limit point compact space, since is an infinite subset of the limit point compact metric space X, E has a limit point, right? E has a limit point. So this limit point, whatever we will get, that will call as x naught. So so let us say this limit point is x naught. So now once again we will use the characterization of limit point. So that says that every neighborhood of x naught intersects, since x naught is the limit point of A, every neighborhood of x naught intersects with A in a point other than x naught, right? So so therefore, so what we will consider now is we will consider the particular open sets around x naught, which are the neighborhoods, right? Basic open sets. So since x naught is a limit point of A for every k belongs to n, b x naught 1 upon k. So this is basically a basic open set centered at x naught minus point x naught will intersects with the set, right? So since x naught is the limit point, this intersection of this set with A is non-empty. So that means it contains a particular element, right? So therefore what we get is for every k natural number k, there exists an element of the set A. What are the elements of A? Elements of A are the sequence elements. It is of the form xn, and that also depend on k because we are choosing the point for k. So that means there exists xn k in A such that this xn k also belongs to this set. So xn k is different from x naught, and xn k belongs to ball center at x naught with radius 1 upon k. So what is happening is, let us see by the diagram. So I have a metric space X, and I have a point x naught here, and x naught is limit point of a particular set A. So what we are considering is we are considering the different lengths. So suppose this is my length 1 around length 1 from x naught, right? So now suppose I take length 1 by 2. So this is 1, this is 1 by 2. So that will be half of this length, right? And then I consider 1 by 3. So I'm considering the small bonds around x naught, and what I'm getting is basically I'm getting 1 by 1 xn k. So my xn 1 belongs to this, then I will get xn 2 belongs to this set, then xn 3 is here, and so on, because what is the condition on xn is xn x naught is a limit point. X naught is a limit point means this set is non-empty, right? So since this set is non-empty, we can always find the terms uh, such that n1 is less than n2 less than n3, so on. So therefore we are getting the sequence, right? So we got the sequence xn k whose distance with x naught is less than 1 upon n. So what we got is that distance of xn k with x naught is less than 1 upon k. So this is true for every k. So now if we take the limit, then as k tends to infinity, what we get is that we get distance of xn k with x naught goes to 0, because this term goes to 0, so this is less than equal to that term, and this is always non-negative, right? So by squeeze theorem, this sequence xn k will converge to x naught, right? So therefore xn k converges to x naught. So using the characterization of the limit point, we have constructed a subsequence of given sequence xn which is convergent. So that will gives us x is a sequentially compact. So let us state the main result which we have proved here, that let x comma d be a matrix space then the following conditions are equivalent. So first condition is that x is compact, and we already proved that it is equivalent to the condition that it is sequentially compact. Right, x is sequentially compact if and only if it is compact. And today what we discuss is that if x is compact, then x is limit point compact, and then we studied x is limit point compact, then it is sequentially compact, and we already know that these two conditions are anyway equivalent. So that will give us proof that all these three conditions are equivalent to each other whenever x is a matrix space. So let us see one example which is which is not limit point compact in the case of matrix space. So we consider infinite set. So you must have studied this set in function analysis, that if I consider the sequence is xn, where each sequence xn is bounded, right? So that means the terms of xn are between two real numbers. If we are taking the sequence of real number, if we take the sequence of complex number, then modulus is less than some fixed number for every term. So that is meaning of the bounded sequence. So this sequence space is a matrix space with respect to this particular metric. So this matrix is nothing but supremum of distance of xi xn with yn. So this is modulus. So basically you can consider this set as a what are the elements. There are if we take R2, there are two elements x1 comma x2, but here there are infinitely many elements, right? x1 comma x2 comma x3 and so on up to xn comma up to infinity. So there are infinitely many terms because it is a sequence. So on that infinite coordinates, basically we are defining this matrix d infinity, and you may have seen that this matrix satisfies cosine squares inequality, and therefore it is a matrix. So this defines a matrix on L infinity. Now we will consider a particular set in this set. So let us consider A, which is subset of L infinity, that is the set of elements En, n belongs to n. So what is En? En is defined as, so every element of L infinity is a sequence. That means each En is a sequence. So what is the sequence? Sequence here is that 0 0 0 up to 0, and we get the term 1, then 0 0 0, so on. So this particular term is basically this number. So this is nth coordinate. So what is En? En is the sequence whose nth coordinate is 1 and all other coordinates are 0. We are considering the set A consisting of all these sets E1, E2, En. So what is E1? E1 is basically 1 0 0, so on. E2 is 0 1 0, so on, in that way. So it is kind of generalization of the orthonormal basis of R2. So what is the special thing in of the set A is each of these sequence is bounded because this is bounded by 1. Right? Only entries are 0 and 1. So they are bounded sequences, and therefore this is the element of L infinity. So A is a subset of L infinity. And now what is meaning of A is bounded? So to prove that A is bounded, we find the distance of En and Em. So distance of En and Em is basically the supremum of the nth coordinate, right? So what is the so let us write here some other index. So let us say j. So enj minus emj. So now what is the possibility of the coordinate of each of En? They are either 0 or they are 1, right? Either the entry is 0 or 1. So that means E and J is either 0 or 1. Same way EMJ is either 0 or 1. So that difference will be either 0 or it will be 1, right? So what will be the supremum? Supremum is 1, because if you take two different n and m, they will differ in at least one coordinate, right? So the distance between en and em is 1 if n is not equal to m. If n is m, then distance is 0, because distance of x with x is always 0. So what we get here is basically we get in particular distance of E1 with each En is 1. So that means what? That means each En is element of A. So this set is subset of the ball center at E1 with radius 2. Right? Because E1 has distance with each En is 1. So they are basically in the on the circle center at E1 with radius 1. So it is already contained in the ball center at 2. So this condition will gives us A is bounded. Bounded set. So bounded means bounded as a subset of the matrix space. It's bounded with respect to the matrix D infinity. And the last thing we want to show is that A has no limit point. So to prove that A has no limit point, first we'll assume that suppose there is a limit point. So limit point in L infinity. No limit point in L infinity. So suppose there is a limit point in L infinity. So suppose there exists, so element of L infinity is a sequence. So there exists a sequence yn, sequence y in L infinity whose terms are y1, y2, yn and so on, such that y is limit point of A. And once again, every limit point, once again we will use the characterization of the limit point of a set. So that will give us, therefore, there exist natural numbers k and l such that the distance of y with ek is less than 1 by 2 and distance of y with el is less than 1 by 2. So what we are saying basically here is that whenever I have a matrix space L infinity and y is the limit point of the set A, right? This set A. So that means whenever I take a ball of a radius half around y, this radius is half, then this always intersect with A in a point. So that point I am writing ek, right? So and in fact this intersection is not only finite, it is in fact infinite, because if I can find a point in the radius half, I can always find a point in a radius 1 by 3 also. I can always find a point, another point EL here, whose distance is also less than half, because it is less than 1 by 3, right? So therefore we get these two elements EL and EK whose distance with y is less than half. So finally what we get is therefore the distance of EL and EK by triangular inequality, it is less than or equal to EL with Y plus Y with EK. And then what we know is the distance of EK with Y is less than half, EL with Y is less than half. So that means it's less than half plus half, which is 1. So what we got is distance of EL and EK is less than 1. But we already observed that the distance is exactly 1. Right? Whatever L and M I take, the distance is always 1 whenever these natural numbers are different. So this is a contradiction. And this contradiction came from our assumption that limit point exists. So therefore, A has no limit point. Right. So I think this should be enough for today's lecture.